group, Mattia, Vittoria and me, are going to talk about optimization today and explain you what it is, why you can use it and how to do it. First of all, what is optimization? Optimization is a mathematical technique to find out where the highest and the lowest points of a function are, called extreme points. Why should you do this? Companies, for example, do it to find out for which price to sell or what quantity to produce in order to maximize profit. There are three basic steps of optimization. The first one is to find the derivative of f of x. Why are you doing this? Because the derivative shows you the slope of the tangent line in a point of f of x. If the slope of the tangent line is 0, it means the tangent line is horizontal. And this means that there is a maximum or minimum point because the graph changes from increasing to decreasing or decreasing to increasing. So in order to find out about this, you just find out the derivative of f of x and equal it to 0. Those are all the possible answers you could get. There is a global minimum and a global maximum point, which means it's the highest or lowest point of f of x in general. You could also get a local minimum or maximum point, which means it's the highest or lowest point, but not of the whole graph of f of x, but only in a closed range domain. And the fifth possible answer is a point of inflection. Another very important thing is to watch out for domains which are given in intervals, because in this case you have to check for the y values of the two endpoints, because those are possible extreme points. For example, here the 0 and the 6 you can see here. 0 is a minimum point, the 6 is a maximum point, so always watch out for that. Okay, in order to find out if you found a maximum or a minimum point, there are two ways to do it. The first one, and most of the times the easier, the faster one, is to do the second derivative test. You just plug in the solutions you got for f of x equals 0 in the second derivative of f of x. And if you get a point which is bigger than 0, you have a minimum point. If it's smaller than 0, you have a maximum point. And if it equals 0, you have a point of inflection. Of course, in some cases, your function is just too big to find the second derivative. So what you do to find out if your extreme point is a maximum or a minimum point. The solution for this is the first derivative test. You have a point f of x. The derivative of f of x is 0, so you know it's an extreme point. To find out if it's a maximum point or a minimum point, you can just try a point a bit on the left of x and a bit on the right of x. For example, you can try if x equals 4, you try 3.9 and 4.1. So if you get as a solution for the derivative of f of x of 3.9 a positive number, you know the graph of f of x is increasing in this point. If it's decreasing in this point, here it reaches a maximum or a minimum, and decreasing after, which means at the point 4.1 for example, you get a negative solution. It means it's decreasing after this point. So you can know that here has to be a maximum point, because the graph is increasing and decreasing after this point x. The same works for a minimum point, it's just exactly the opposite. If you get a positive number on both sides or a negative number of both sides, you know the graph is increasing, reaching the point 0 where extreme point is, and then increasing again or decreasing again, you know it's a point of inflection. The third step of optimization is to find out if it's an absolute or local minimum or maximum point. Therefore, first you have to look for two things, because if one of those two things appears in the graph of f of x, you don't have an absolute maximum or minimum point. The first is look for vertical asymptotes, and the second one is study the behavior towards infinity. Here's an example for a graph with a vertical asymptote here in this point. You have a local minimum point here and a local maximum point here, but there's no absolute extreme points because the graph is going much higher here than the local maximum point here. And the same happens here with the minimum point, and the graph is going towards minus infinity here. And here, a second example for the behavior towards infinity. If the graph is coming from plus infinity, going down here, reaching a local minimum point, local maximum point, and going back to minus infinity, you also don't have a absolute maximum or minimum point.
Economic equations consist of these formulas. The first one is price per unit, which is represented by P of Q. Quantity is represented by Q. Revenue is calculated by multiplying P and Q. Total cost is just represented by C of Q. And to determine the profit, you do revenue minus cost. And in order to find revenue, you do P times Q. Then, to find the average cost, you do C divided by Q. To find the marginal cost, you just find the derivative which marginal cost is the cost of producing an additional unit on a certain price level, and then marginal revenue is just done by finding the derivative or revenue.
Okay, so if we have two equations, which in this case is C of Q, which is total cost, and is Q to the power of 3 minus 8Q squared plus 20Q minus 2, and then the price function with price of Q, which is 20 minus 2Q, which is the price per unit when Q units are being sold. So we want to find the number of units that maximize total revenue. So first thing we need to do is to find the revenue equation. And we know that revenue equals price times quantity. In this case, we know the price, which is 20 minus 2Q, and we want to multiply it by Q. So we have revenue is going to be 20Q minus 2Q to the power of 2. Now, second thing we need to do, since we want to find the number that maximizes total revenue, is that we need to do the first derivative of revenue and put it equal to 0. So the first derivative of revenue is found by doing the power rule, which in this case is going to be 20 minus 4Q. And now we need to solve for Q. And we have that the quantity that the company needs to solve the quantity that the company needs to sell in order to maximize revenue is 5. If we want to check that this is a maximum number, we can use the second derivative test, which was explained before by Korbi. Therefore, we find the second derivative of the first derivative of the revenue equation, which is, by always doing the power rule, it's minus 4. So when the second derivative is less than 0, it means that it's a maximum. Therefore, Q of 5 is a maximum. If you want to even double check more, you can even graph it, and you will see that the graph will look like this. Where the maximum value is found when quantity is at 5. So it was quantity. But instead, if we want to find the maximum profit in the value of Q at which it is achieved, we first of all need to find the profit equations, which is revenue minus cost, as we seen before. To differentiate from price, we use capital letter of B. So revenue minus cost, we have the revenue function we found before, minus the cost function. And since there is a negative sign in front, all the signs will change. Now we simplify. These two we cancel because they have opposite sign. Negative Q to the power 3 stays the same. This will simplify, it becomes 6Q to the power of 2 to the minus 2. Now, if we want to find the maximum profit, we need to use the first derivative. So we have to plug in the first derivative function of Q equal to 0, which will become negative 3Q to the power of 2 plus 12Q, always using the power rule. Yes. Now we need to solve for Q. We take out the common factor, which is negative 3Q, and this becomes Q negative 4. And we solve for Q, with Q is equal to 4 and Q equal to 0. If we want to see now if Q equal to 4 is a maximum point, we need to use the second derivative test in this case. In this case becomes negative 6Q plus 12 when Q equal to 4 equal to negative 12. And we know that when the second derivative is less than 0, it's a maximum value. Therefore, profit is maximized when quantity equal to 4. We didn't choose quantity is equal to 0 because if we do the second derivative of the profit equation with quantity equal to 0, we found that it's a positive result, therefore it's a minimum value, but we're looking for the maximum profit. We found a quantity that will maximize profit, which is when quantity equals to 4. But to see how much profit it will generate, we need to plug 4 into Q in the profit equation, which will become negative 4 to the power of 3 plus 6 4 to the power of 2, negative 2, which is negative 64 plus 96 minus 2, which is equal to 30. Therefore, the profit will be 30 when quantity is 4, and this will be the maximized profit of the company. So, if we want to determine the price and maximize profit, we know that the profit is maximized when quantity is 4, therefore we put 4 into the equation of price per unit. So, price 4 is 20 minus 2 times 4 is 20 minus 8, which is 12. Therefore, the price that will maximize profit is 12 and the quantity is 4.
The law states that the profit maximizing level of output is marginal cost is equal to marginal revenue. Now, let's say point A. At point A, we see that marginal revenue is at this point while marginal cost is at this point. This means that the company is making profits, however, it still has the possibility to make further profits, so there's no reason to operate here when it can operate here. Then at point B, let's say we're at this level, we see that MC is above marginal revenue. That means that the company is making losses. Therefore, it is not a level of output that you want to produce because you won't be making profits at all. So the solution to that is to just decrease your output and to go to that level, which justifies the reason to operate at this level where MC equals MR.